Mankind's journey into space, like every great voyage of discovery, will become part of an unending journey of liberation. Greetings to all, I'm Sarvesh, Chief Supporter of Kumari Onion Development. Today is the fifth day of celebrating World Space Week, along with Indian Institute of Space Science and Technology and Kumari Onion Development. October 8, 1958 was the day the National Aeronautics and Space Administration (NASA) was established, replacing the National Advisory Committee for Aeronautics. Touch the sky with glory. Every year on October 8, India observes Indian Air Force Day to pay tribute to the brave servicemen and pilots who have sacrificed their lives for the nation. This day marks the formation of the Indian Air Force and is a time to honor the courageous individuals who selflessly serve the country, participating in vital missions and humanitarian. Yesterday, on the topic space technologies and opportunities in India, we gained immense knowledge on the history of Indian Space Research Organization and opportunities we could get to participate in the field of space science. I invite Mullachery M. Vene, organizer of Kumari Arivu Therival, to the webinar. It's my pleasure to invite Ms. Xeel Gabina, a BTech scholar from IIST, to present the introductory address.
Good evening, everyone. This is Xeel Gabani from Indian Institute of Space Science and Technology. I'd like to welcome Dr. Anand Narayanan with a short introduction about him. Dr. Anand Narayanan is a professor at the Indian Institute of Space Science and Technology, Thiruvananthapuram. Previously, he was a postdoctoral scholar. I'm sorry, is it Equin? Yeah. Previously, he was a postdoctoral scholar in the Department of Astronomy at the University of Wisconsin-Madison in the United States. He earned his PhD and Master of Science in Astrophysics from the Pennsylvania State University in the United States. He holds a BTech in Electrical and Electronics Engineering from the College of Engineering, Thiruvananthapuram. His research involves understanding how galaxies and other large-scale structures form in our universe. I now invite you, sir, to deliver the talk.
Thank you. Thanks so much, Xeel, for the introduction. Yeah, sorry, Sarvesh, go ahead.
No problem, sir.
It's okay. You wanted to say something?
No. Thank you, ma'am. With unparalleled enthusiasm and satisfaction, I invite Dr. Anand Narayanan, Professor of Department of Earth and Space Science, IIST, to speak on the topic Exoplanets and Search for Habitable World.
Okay, yeah. So it's over to me, right?
Yes, sir.
Yeah, so thank you, Xeel. Thanks for that nice introduction. And thank you, Sarvesh, for putting together a very nice introduction of what this International Space Week is about. That was a short, crisp presentation on why we are celebrating this International Space Week. So it's my honor, it's my privilege to spend some time with all of you through this virtual platform as the whole world is celebrating human foray into space. How research in space science and space technology has benefited humankind, how it has propelled us into an era of progress. As I understand, mine is only one talk in a series of talks that you have been listening to and which you are going to listen for the rest of the week also. As Xeel mentioned, I am a faculty member in the Department of Earth and Space Sciences at IIST. I teach and I do research at IIST. The subject that I teach is astrophysics. I'm sure since all of you are science enthusiasts, you know what astrophysics is, but let me just quickly explain for those of you who do not know what astrophysics is. It's basically a discipline of science. It's a discipline of physics. So what we try to do in astrophysics is we use the fundamental laws of physics, the fundamental principles of physics to understand the physical universe, the universe at large. So that means we use the kind of laws of physics, laws of science that you are learning in school to make sense of the world around us. So that includes even the world above us. So that means planets, stars, moons, star clusters, nebulae, galaxies. What are those objects? How did they form? What kind of evolution process do they go through? And finally, the universe at large. So that is what we try to do in astrophysics. And so that's the subject that I teach at IIST, and I do research at IIST. And I know that in the past, Sir has brought many students as part of this Kumari Ariviyal Peravai program to IIST, and I've had the pleasure of interacting with many of the previous batches of students. I hope that Sir will be bringing students this year also, or maybe next year. It's always a pleasure to have Sir and students in our campus. So with that, let me quickly jump on to my presentation. I'll start sharing the slides. And one of you can tell me whether I'm showing a white screen. Is that white screen visible?
Yes, sir.
Yeah. Okay, so before we go on to the presentation, let me just also mention that I would request all of you to mute your microphones so that voice doesn't come through while I'm presenting. And the other thing is, we are at the mercy of internet technology. So even though the internet at my house is okay, in case if there is any problem with the internet, if I drop out of the call, I will try to rejoin as quickly as I can. Okay. So in case there is any technical glitch. So, so the topic that I'm going to be talking about is, as Sarvesh was mentioning, it's extrasolar planets and the search for habitable worlds. So if you look at astrophysics, astrophysics deals with some of the most profound questions that the human species has ever asked, which is, does our universe have a beginning? Will it ever end? How old is our universe? Does our universe have any boundaries? What is the nature of time? How matter was created? So these kind of large questions we are trying to find an answer to using in this field of astrophysics. And one of such big questions that astrophysics deals with itself is whether are we the only sentient beings? Are we the only intelligent beings in this entire universe who are asking these kind of questions? In other words, could there be life anywhere else in the universe beyond the confines of Earth and even beyond the confines of the solar system? Could there be life anywhere else in the universe, and sometimes even intelligent life? So that is what the subject is about. Are we alone in this universe? I'm sure many of you would have asked this question yourself. You know, if when you look at a starry night sky, and if you stretch your imagination, definitely this kind of question is going to pop up in your mind, whether we are alone in our universe or not. And so an answer to this question would involve finding the right kind of environment where life can exist, where life can evolve, where life can thrive. And the life as we know it here on Earth requires a planetary environment, requires a planet. Life as we know it here on Earth cannot really survive in interstellar space. Life as we know it here on Earth cannot survive on the surface of a star where the conditions are very hostile. So the kind of abundant life that we see here on Earth requires a very safe, protective environment of a planet. Therefore, if you want to answer this question of whether we are alone in this universe or not, or whether there could be life anywhere else in the universe, the first step towards answering this question is to find planets revolving around other stars. Are there planetary systems beyond the solar system in other parts of the universe? Are there planets orbiting other stars? So in astronomy, planets that are orbiting stars other than the sun, they are collectively referred to as extrasolar planets or exoplanets for short. That is a terminology, that's the term that is used to talk about all planets that are orbiting stars other than the sun. So what I'm going to talk about in the next 40 minutes or so is one of the greatest adventures that has been unfolding in the field of astrophysics in the last 3 decades or 4 decades, which is the humankind's effort to discover planets around other stars and to speculate on the possible habitability of those planets, to hypothesize on whether those planets could be supporting life or not. So that is the story that I'm going to be talking about. So I hope these slides are visible. Right now I'm showing a slide which says extrasolar planets and the search for habitable worlds. It's visible, right?
Yes, sir.
Yeah,
Yes.
thank you.
Yes, sir, it is
So,
visible.
thank you. So if you now what you're looking at in the slide is a picture of the night sky taken from a place called Hanle in Ladakh. And in the foreground, you are seeing an observatory that is owned and operated by the Indian Institute of Astrophysics in Bangalore. But that is not the point of this picture. The point of this picture is the sky, which is full of stars. Okay, so for a very long time, astronomers knew that sun is only one star in a huge collection of nearly 200 billion stars that forms the Milky Way galaxy. And sun is only one star in that 200 billion star collection. So there's nothing peculiar or nothing important that makes sun a very important star. So there's no reason why only sun should have planets revolving around it. So astronomers for a very long time, they knew that there has to be planets orbiting other stars. But as it turns out, it's not very easy to discover these extrasolar planets or exoplanets, that is planets orbiting other stars. There are some observational challenges, there are some barriers in finding planets around other stars. So let me talk about what are those observational barriers or challenges in discovering extrasolar planets. This picture, some of you may have already seen it. This is a picture that was widely circulated in WhatsApp and through social media for many years. This picture shows the sun and the planets of the solar system drawn to scale. That means the relative size of the sun and the planets is accurate. Okay. So if you think of the sun as a big ball, like this orange ball, like a basketball or something, then you can see how tiny the planets of the solar system are. The biggest planet in the solar system, which is Jupiter, you can see that it looks like a small marble when compared to the sun, which looks like a big basketball. So Jupiter, which is the biggest planet in the solar system, is still 10 times smaller than the sun. And Earth is 100 times smaller than the sun. So what I'm trying to say here is that planets are very small compared to stars. Their sizes are very small compared to a star. And combined with this is the extra difficulty that the stars that we see in the night sky, okay, all the stars that we see in the night sky, which belong to our Milky Way galaxy, they are at tremendously large distances from us. The stars that we see in the night sky are 100 or 1,000 or tens of thousands of light years away from us. Now, many of you may know what a light year is. A light year is a distance that light travels in 1 year. In our universe, there's nothing that can travel faster than light. Light covers a distance of 3 lakh kilometers. That is 300,000 kilometers in 1 second. That is the speed which light travels. To put it in perspective, that number, 300,000 kilometers in 1 second, what that means is a light particle, a photon, can go around the Earth 7 times in 1 second. So 7 times the circumference of the Earth is 300,000 kilometers. Okay, so it can go around the Earth 7 times in 1 second. That is the speed at which light travels. And at that ridiculously high speed, light would take 100 or 1,000 or tens of thousands of years to reach us from these distant stars that we see in the night sky. Which means that when you look at the night sky stars, even with the biggest telescope that you can access, because of the large distance that separates us from these stars, even stars look like dots, look like point sources, like small dots, even when we look at it through big telescopes. Just as when we look at the stars with our naked eye, stars looks like small dots, even with big telescopes, stars are going to look like small dots, because even though a star is a big object, they are so far away that their angular size is very, very small. So planets which are anyway smaller than a star they are going to have a size that is smaller than a point, if there is such a thing as something that is smaller than a point. Okay, so planets are going to be very small, and combined with that, there is this extra difficulty that a star is extremely bright when compared to a planet. In the part of the electromagnetic spectrum that the human eye can see, which is what we refer to as visible light, a star is usually million times more brighter than a planet. A million is 1 followed by 6 zeros. That is what a million is. So what that means is, when you point your telescope and try to take a picture of the night sky, you will easily see the stars because they are very bright. You will see them as point objects, but you will see them because they're very bright. But a planet which is sitting right next to that star and orbiting that star, it is going to be a million times fainter than the star. So to give you an example, it is like, if you think of a stadium floodlight, in a football ground or in a cricket ground, you have usually floodlights that illuminate the ground during night. Typically, those lamps are 1,000-watt lamps. So if you now imagine that a floodlight is switched on, and right next to that, there is a small LED light that is glowing. Okay. So if you try to take a picture of it, the glare from the floodlight will completely wipe out the light from the LED. So you will not see the LED light that is shining next to the floodlight because of the glare from the floodlight. That's the same challenge that astronomers face when they try to take pictures of extrasolar planets. When they try to discover extrasolar planets, the light from the star is so much that it will block or it will glare out the light from the planet. So what that means is, directly taking pictures of extrasolar planets is not easy. It's not trivial. Fortunately, there are some indirect methods for discovering extrasolar planets. I'm going to be talking about 2 such methods which have been very successful in helping astronomers to discover extrasolar planets. Both of them are indirect methods. And why they are called indirect methods is because in both these methods, which I'm going to be talking about very soon, in both these methods, we don't see the planet directly. We don't see the extrasolar planet. Our observation with the telescope is on the star. Based on the property of that star, based on the behavior of that star, we come to the indirect conclusion that there is a planet that is revolving around that star. So even though we have not seen the planet, circumstantial evidences tell us that there is a planet orbiting around that star. So by observing the star, we make the inference, or we make the conclusion that there is a planet. And the 2 methods that I'm going to be talking about is, one is called radial velocity method, and the other is called the transit method. These 2 are indirect ways of discovering extrasolar planets, and so far, maximum number of extrasolar planets have been discovered through one of these techniques, radial velocity method and transit method. There are actually many more methods which are also indirect, but these 2 are very special because they are being most successfully used. So let me explain the basic physics behind radial velocity method first, and then I will talk about transit method. So generally in school, when we study planetary systems, what we learn is that planets are revolving around stars. Like in the case of our solar system, we'll say all the planets are going around the sun. But that statement is not fully accurate. If you take a star-planet system, there is a point where the forces from the star on the planet and the planet on the star, that those forces are going to be equal. Gravitational force that the star exerts on the planet, and the gravitational force that the planet in turn exerts on the star, they are going to balance out. And that point is called the center of mass. Sometimes it's also called barycenter. And the planet is actually revolving around this barycenter. Okay, and usually, since stars are much more massive than a planet, this barycenter or the center of mass is very close to the star, often inside the star itself, which is why we very loosely say that planets are revolving around stars. But you can think of a scenario where the center of mass is slightly outside. Okay. So in that case, what happens is, as the planet revolves around the center of mass, the star will not be stationary. It will also be revolving around the center of mass. Only then it will be a stable system. So what you are seeing here as a video, it's an animation. It's not real data. It's not real star and real planet. It's just an animation that shows a planet revolving around the center of mass of a star-planet system. And similarly, the star is also revolving around the center of mass of the star-planet system. Okay. Are you able to see this animation in an okay way, or is the internet quality affecting? Okay.
Okay, sir.
Okay,
sir.
Yeah. Yeah. Thank you. So what in radial velocity method, what astronomers do is they try to measure this motion of the star to understand that whether there is a planet around it or not. Now, if there is no planet around that star, then there is nothing that is gravitationally pulling the star. There is no center of mass concept there. So therefore, the star is going to be stationary. But if there is a planet orbiting around that star, because of the gravitational pull from the planet, the star is going to go around in tiny circles as shown in this animation. So this motion of the star is called wobble motion. Sometimes it's called wobbling in a very colloquial sense. Sometimes it's also referred to as reflex motion. These are terms used for the same thing, which is the oscillatory motion of the star, the circular motion of the star around the center of mass. That's called wobble motion or wobbling or reflex motion. Now, it is this wobble motion or wobbling or reflex motion that astronomers measure for the star, which tells us that there is a planet orbiting around it, even though we have not seen the planet. So how is this wobble motion measured? When we look at the night sky, the stars are so far away that even if the star is exhibiting this wobble motion, we will not be able to see it just by looking at the star. We need to do some careful measurements. The signal that we get from a star is the light that the star is emitting. So what astronomers do is they carefully study this light, they analyze this light in all possible ways, which helps them to understand whether the star which is emitting the light is actually wobbling, whether it is oscillating or not. And the observation that they do is an observation that I think many of you would have done in school, which is to use a prism to send white light through it. When you send a white light through a glass prism, you see the rainbow of colors on the other side. The rainbow of colors that you see on the other side, it is called the spectrum of the white light. That is the word that is used. It's called the spectrum of white light. So what that means is the white light is made of these colors, is made of these 7 colors. And when it passes through a glass prism, the glass prism disperses or separates the light into its component colors. And you get a spectrum. So to measure the reflex motion or the wobbling of a star, what astronomers do is they use the telescope to collect the light from the star, and they send that light to an instrument called a spectrograph, which has a equipment like this prism inside, and it produces a spectrum of that star. Okay, so that is explained through this animation. So this is an animation again. This is not a real astronomical image. You have a star here and a planet here. Remember that in radial velocity method, we don't see the planet. Our observation is confined to the star. But for the sake of our understanding, in this animation, they have shown the planet also so that we understand the concept. The bottom, you see a rainbow of colors. That is basically the spectrum of that star. So some telescope is looking at that star, it is collecting the light, and it is sending that light to a spectrograph, which produces this rainbow of colors. Now watch what happens when I play this animation. So the planet is going around the center of mass of the star-planet system. The star is also going around the center of mass of the star-planet system. The star is not stationary, it's wobbling. So because it is wobbling, you see that in the spectrum, you see that the spectrum is also shifting towards blue, shifting towards red, shifting towards blue, shifting towards red like this. I will play the animation once again. You can see that the spectrum is shifting in its colors, like from blue to red to blue. It is there. The spectrum is also oscillating like this. So this effect is called Doppler effect. Now, students who are in higher secondary school, classes 11 and 12, you may have heard of Doppler effect of light. If you have not heard of Doppler effect of light, you can write it down and later on you can go and look it up online. The spelling is Doppler, Doppler effect of light. And what Doppler effect of light in physics says is, when a source, when an object that is emitting light is moving with respect to the observer, then we are going to see this periodic shift in that spectrum of that light from blue to red to blue to red, back and forth, which tells us that the object is not stationary, but it is oscillating like this. So it is this spectroscopic observation that astronomers do which helps them to understand that there is a wobble motion for that star. And based on that wobble motion, they infer the properties of the extrasolar planet around that star, which they have not seen. Their observation is only on the star, but they, using that star's wobble motion, they infer that there is a planet. And by carefully studying the spectrum, they can determine a number of properties of the unseen planet around that star, even through this process. So the properties that they can learn about the extrasolar planet using radial velocity method is, they can determine how massive the planet is, whether it is a big planet like Jupiter or whether it is a small mass planet like Mars or Earth or Venus. They can determine that. They can determine how far away the planet is from the star by studying this wobble motion through spectroscopy. So whether the planet is very close to the star or whether the planet is very far away from the star, this they can learn. They can learn how long it takes the planet to go around the star, whether the planet takes 30 days, 30 Earth days to go once around the star, which means 1 year of that planet will be 30 Earth days, or whether it's going to take 700 Earth days to go around, which means the planet is farther away and it's taking a long time to go around the star. How long does it take? And finally, by studying the wobble motion, astronomers can also understand what is the shape of the orbit, whether the planet is going around the star in a circular orbit, or whether the planet is going around the star in a slightly elliptical orbit, slightly eccentric orbit. All these things we can learn. So radial velocity method, even though it does not show you the planet, our observation is on the star, but by looking at the star, we can learn all these properties about the exoplanet around that star. That is radial velocity method. Let me now go to the second method, which is transit method. So in transit method, remember, transit method is also an indirect method. Here again, we don't see the planet. Our observation is on the star. Based on some behavior of the star, we infer the presence of a planet around it. In radial velocity, we were measuring the Doppler motion or the wobble motion of the star. In transit method, what we do is we continuously monitor the brightness of the star. So what you're going to see is an animation again. In this animation, you can see that we are measuring the brightness of the star. And when we are measuring the brightness, a planet that is revolving around that star passes in front of that star when we are looking at it. So when it passes in front of that star, for that brief duration of transit, it is called transit. When some small object passes in front of a bigger object, that is called a transit. So when the planet transits in front of the star, for that brief duration, the planet will block a little bit of light from the star. And the brightness of the star will slightly dim. And when the planet moves out of the field of view, out of our line of sight, then the brightness again comes back to the normal value. Okay, so this is an animation. Remember, in the transit method, we don't see the planet. To make us understand the concept of what transit method is, in this animation, they have shown the planet. Otherwise, the star itself looks like a dot in the sky. So a planet which is moving in front of that star will be smaller than a dot and we will never see it. All we will see is there is a dip in the brightness of that star. And that dip in brightness will be repetitive. It will repeat in regular intervals of time because the planet is going around that star, and every time it passes in front of that star, it will produce a dip in brightness. So repetitive, repeated dips in brightness of a star is the signal that we use to understand that there is something that is moving in front of the star that is blocking the light. Now, sometimes there can be a small planet and a bigger planet that is revolving around a star. There can be multi-planet exoplanet systems. So if it is a small planet, then as shown in this animation, we will get a small dip in the brightness. If it's a big planet that is transiting, then we will get a bigger dip in brightness. That is what is shown in this animation. Again, this is an animation to help us understand the concept of transit method. Okay. So in transit method, what we can learn about is based on how deep the dip is, we can understand what is the size of the planet. If the dip is very large, then that means that it's a big planet. If the dip is small, then that means that it's a small planet. So we can determine the size. In radial velocity, we could determine the mass of the planet. Using transit method, we can determine the size, whether the planet is big, like our gas giant planets like Jupiter, Saturn, Uranus, Neptune, etc., or whether it's a small planet like Mercury or Venus or Earth or Mars. We can also determine whether the orbit in which the planet is revolving around the star has any angle with respect to the sky. We can determine that. We can also determine how long it takes for the planet to go around the star, whether it takes a long time or whether the planet is going around the star in a very fast way. So these are the two techniques, radial velocity method and transit method. And both these techniques are indirect ways of discovering extrasolar planets, planets revolving around other stars. Now, they are both indirect. So we have not seen the planet. What would be really interesting, what would be really exciting is if we could actually see the planet for real. That will be the most convincing evidence for the existence of exoplanets. As I told you in the beginning, there are some challenges, there are some barriers in discovering planets around other stars, directly seeing planets around other stars, because one is that star itself is a point, so planet is going to be smaller than a point. The other is that the stars are extremely bright when compared to planets. So planets which are sitting very close to the stars in the sky, they will be lost in the glare of the star. So this makes direct imaging or direct photography of extrasolar planets a difficulty. It is like seeing a firefly. You know what a firefly is, right? A firefly is this glowing insect. You may have all seen it. On some dark nights, you can see these glowing insects. So it is like seeing a firefly. You can think of a firefly as an LED light also that is sitting next to a floodlight. It is like that. If you are trying to take a picture of a firefly that is sitting next to a floodlight, you will never see that firefly because the floodlight will completely glare out the image. So, but it is now possible through the developments in technology to actually discover extrasolar planets using direct imaging. Okay. And now, so what I'm going to do is I'll just skip a couple of these slides and I'll just show you the results. In the last 20 years or so, with improvements in optics technology, optics is this branch of physics that deals with the study of light. Optical engineering is this discipline of engineering combined with physics, where you try to design new instruments that can be used to study light in more and more sophisticated ways. Okay, that's optical engineering. So with improvements in technology, improvements in optical engineering, it has now become possible to take pictures of extrasolar planets, even though they are very faint and they are sitting very close to very bright stars. So I'm going to show you now real astronomical data. So far for radial velocity and transit method, what you were looking at were animations mostly to explain the concept. Now we are actually seeing extrasolar planets. So here is one, HR 8799, which is written at the bottom of the slide. That is the name of a star. Stars usually, most stars don't have names like Betelgeuse or Orion or Ardra or any of those things. Only very few stars have unique names. Most of the stars have catalog numbers. It's like, all of us have this Aadhaar number, right? Which is a unique ID. Similarly, in catalogs, stars have a number. So this particular star belongs to this HR catalog, and it is the 8,799th object in the HR catalog. And so that star is what you are seeing in the middle of it. Okay. So is this mouse pointer visible? I don't know whether in Zoom you can see the mouse pointer or not.
Yes, sir, it is visible.
Sir, it is visible.
Okay. So this is what the star is. Okay, and it does not look like a star, because what they have done is, after taking the picture, they have tried to remove the light from the star so that they can see the objects near the star, which is where the planets are going to be. So they have tried some image processing techniques here. And when you subtract out the light from the star, you see there are 4 glowing objects, B, C, D, E marked here. These 4 objects have been identified as 4 planets that are revolving around the star HR 8799. What you are looking at here is real photograph of extrasolar planets. Now, as you can see, we are not able to see much detail. For example, we don't know whether any of these planets have rings like Saturn, whether any of them have banded structures like Jupiter, whether any of them have dense clouds. We don't know that, because remember that these stars and planets are light years of distance from us. So they only look like point sources. They only look like dots. We cannot get any further detail. So B, C, D are 4 extrasolar planets. And the way we know that these are planets revolving around the star HR 8799 is, if we keep on observing the system for many years, you can actually see them revolving around the star. So you are going to now see an animation. This animation is very short, but the animation is made by putting together real astronomical data spanning 7 years. So in the bottom of this image, you can see 2009, July 31st written. 31st/07/2009 is 31st of July 2009. And when I play this animation, this 2009 will change all the way to 2016. So that means it's 7 years of observations. And in the center is the HR 8799 star. And around it, you can see 4 small bright objects. That is B, C, D, E, those 4 planets. So let me play the animation. Just watch closely. Okay, I'll play it once again. So 7 years of observations is showing us those 4 planets revolving around the star HR 8799. So you are actually seeing an extrasolar planetary system here, real data, with the planets revolving around the central star. I will show you one more example. Beta Pictoris is the name of a star, and that star is in the center here, shown as a black circle. The reason why it's shown as a black circle is because the light from the star has been removed from this image using image processing technique, so that we can see planets around it. And what you see over here is a planet that is revolving around the star Beta Pictoris. 2013 is the year, and watch what happens when the animation is run. So 2014, 2015, 2016, if you continuously observe, you will see the planet revolving around the star. You don't see the full orbit, because for that you need to keep on observing the system for even more number of years. Here it is only data for about 3 to 4 years. You can see the planet moving relative to the star. So we have now started getting images of extrasolar planets. Now, as we speak, just to give you an idea, the first extrasolar planet was discovered in the year 1995. From 1995 to 2014, it's roughly 30 years, 25 to 30 years. In that short span of time, 25 to 30 years is not a very long period when you consider how difficult these observations are and sometimes how slowly science progresses. So in that span of 2 to 3 decades, astronomers have discovered more than 6,000. In this slide, it says 5,000. That is because the slide is a little old. Now, astronomers have discovered more than 6,000 planets orbiting different stars in our own Milky Way galaxy. Some of these planets are orbiting the same star. So, the planets belong to multi-planetary systems. Some of them are belong to stars where there is only one planet that is discovered. And a lot of these planets that are discovered are big gaseous planets like Jupiter. But still, along with it, some low mass planets like Earth mass planets have also been discovered. So in a short span of time, literally there has been a huge increase in the number of extrasolar planets that have been discovered. Prior to 1995, the only planetary system that we knew of was our own solar system, with the sun and the planets revolving around it. 1995 is when the first extrasolar planet was discovered. From then, there has been an explosion of data in this field. Like every week, every day, new extrasolar planets are being discovered. So that brings us to this question. Now that we are routinely discovering extrasolar planets, are any of those planets Earth-like? What I mean by the Earth-like is whether any of those planets have conditions that are favorable for life to exist. Now, that's a very interesting question for which many people are interested to know the answer to. Even the general public is interested to know whether any of those extrasolar planets are habitable. Habitable meaning whether it can support life. And the only example of life that we have so far is life on Earth. And if you look at life on Earth, we can say that for the vast majority of life on Earth depends on liquid water. The presence of water in its liquid form is a necessary condition for life to exist. The other necessary condition for life to exist is the presence of a dense atmosphere. The atmosphere of Earth protects us from harmful ultraviolet radiations from the sun. It also provides us with the air that we breathe. Also for plants, the air that they breathe comes from atmosphere. So an atmosphere seems to be one of the prerequisites for life. And the presence of water in liquid form seems to be the other prerequisite for life. So right now, in the field of extrasolar planet research, astronomers, in addition to discovering extrasolar planets, they are also trying to see whether they can assess the conditions that are prevailing in those extrasolar planets and whether they can make an assessment on whether those planets are habitable or not. Remember that these extrasolar planets that astronomers are discovering around other stars, they are 100 or 1,000 or tens of thousands of light years away from us, which means that it is not possible to send a spacecraft to those extrasolar planets and take pictures and send it back to us, because even if the spacecraft travels at the speed of light, which is not possible, but hypothetically speaking, even if those spacecraft could travel at the speed of light, it will take 100 or 1,000 or 10,000 years to reach those extrasolar planets. And then if they take a picture and send it back to us as electromagnetic radiation, that electromagnetic radiation is going to take 100 or 1,000 or tens of thousands of years to reach us. So it's not feasible with the current propulsion technology to send spacecraft to these extrasolar planets. All we can do is sit here on Earth and study these extrasolar planets and try to see whether we can make an educated guess on whether these planets are supporting life or not. So what is happening in the field of extrasolar planet research currently? What is the frontier area of research there? I'm going to explain that and then I will close my presentation. So what astronomers are now trying to do is, in addition to discovering these extrasolar planets, they are also trying to see whether those planets have an atmosphere or not. And if they have an atmosphere, then they are trying to understand what is the chemical composition of that atmosphere. And the reason why the chemical composition of the atmosphere is so important is because what kind of molecules are present in a planet's atmosphere can be used to infer whether the planet has life or not. So let me explain that with the help of taking an example from our own solar system. So here is sun, and in the three strips, what you're looking at are actual images of Venus, the surface of Venus and the atmosphere of Venus. Mars and the atmosphere of Mars, and Earth and the atmosphere of Earth. So you can see that Venus, Earth, and Mars, which are inner planets of the solar system, they are roughly at the same distance from the Sun. Venus is a little closer to the Sun than Earth is. Mars is a little further away from the Sun than Earth is. But approximately they are at the same distance. So even though these three planets are roughly at the same distance from Sun, Earth is very different when compared to Mars and Venus. There are a lot of similarities in the atmospheres of Venus and Mars. Venus has a very thick atmosphere, Mars has a thin atmosphere. But if you look at the chemical composition of atmosphere of Venus and Mars, the atmosphere, the dominant gas is carbon dioxide, followed by a little bit of nitrogen. Whereas if you look at the atmospheric composition of Earth, on Earth, oxygen is a very abundant molecule. In Earth's atmosphere, oxygen is a very abundant molecule. In fact, 20% of the Earth's atmosphere is made up of molecular oxygen, O2, which is what we breathe, okay, and which is what plants give out during their metabolism, during photosynthesis. So O2, which occupies 1 part in 5, that is 20% of Earth's atmosphere, is an abundant molecule in Earth's atmosphere, which is completely absent in Venus and Mars. So now the question is, if Mars, Venus, and Earth are all roughly at the same distance from the Sun, then how come Earth has such a different atmospheric composition when compared to Mars and Venus? The answer is, what geologists and people who study climate, Earth's climate, and how it has evolved over time, over thousands and millions of years, what they tell us is that when our solar system formed 4,500 million years ago, when Mars, Venus, and Earth were very young planets, all three planets had a very similar atmospheric composition. Roughly 2,500 million years ago, that is 2.5 million years ago, the first life forms on Earth originated. These life forms were microorganisms. They were not big evolved mammals or anything. They were microorganisms. Generally, these microorganisms are blue-green algae, which are found in oceans. Cyanobacteria, which were also found in oceans. They formed in oceans. Phytoplankton, which are sea plants. These small microorganisms life emerged. And these microorganisms, they underwent metabolism, or they executed metabolism. Metabolism meaning the process by which they produce energy so that they can thrive, survive. Their metabolism involved taking carbon dioxide from the atmosphere along with the help of sunlight, etc., and then do the metabolism process and give out oxygen as a byproduct. So this is very similar to what plants are doing right now. So these early microorganisms had this anaerobic kind of metabolism process. And so when these microorganisms started multiplying and growing, each microorganism as part of its metabolism started pumping oxygen into the atmosphere, gradually raising the abundance of molecular oxygen in Earth's atmosphere to its present value, which is 20% of Earth's atmosphere. This is called the Great Oxidation Event. GOE, Great Oxidation Event. And this Great Oxidation Event happened roughly 2.5 billion years back in the history of Earth. So if life on Earth were to vanish today, if all life on Earth were to completely vanish today, including plants and marine life forms, all the oxygen in the Earth's atmosphere, within a span of a few thousand years, they will completely vanish, because that oxygen will either react with minerals on the Earth's surface and they will produce oxides, or they will get dissolved into Earth's oceans. What keeps the oxygen abundance in the Earth's atmosphere at 20% is the presence of life forms which are giving out oxygen as part of a metabolism, which is marine phytoplankton, cyanobacteria, etc., and also the plants that we see on land. So in other words, what that means is the presence of oxygen in Earth's atmosphere is an indication that Earth has life in it. Earth has a biomass. So oxygen is therefore referred to as a biomarker molecule. Biomarker meaning the presence, it acts as a marker, it acts as an indicator that there is life on that planet. There are similarly other biomarker molecules. Ozone, O3 is a biomarker molecule. Methane, CH4 is a biomarker molecule. Water vapor is a biomarker molecule. So the presence of many of these biomarker molecules in an exoplanet's atmosphere. Suppose we discover an extrasolar planet, and if we can detect its atmosphere and the chemical composition in that atmosphere, and if that atmosphere shows presence of biomarker molecules like oxygen, ozone, methane, water vapor, etc., then it is an indirect indication that that is a habitable planet and there is possibly life on that planet, because the source of these molecules in the atmosphere is life itself. So that is where the field of research is right now. So finally, I want to leave you with this slide. So this field of research in extrasolar planets is fast developing, it's fast growing. There are a lot of very interesting discoveries that are happening on a daily basis, as I mentioned. If you read online, there is plenty of material online that explains this fascinating field of discovery of extrasolar planets and the quest for habitable worlds. But one thing, if there is one lesson that we can carry forward with us from this effort by astronomers for the last 20 to 30 years in this field, if there is one lesson that we want to remember or want to take away, it is the following. As I mentioned, prior to 1995, the only planetary system that we knew of was our own solar system, with sun and the planets revolving around it. But in the last 25 to 30 years, astronomers have discovered more than 6,000 extrasolar planets by looking at some of the stars that are near to us. So what this field of research is suggesting is that every star possibly has one or more planets revolving around them. Formation of planets seems to be something that happens naturally when stars form. When stars are formed, planets also form around them, which means every star has one or more planets revolving around it. It's only a matter of discovering them. And as I mentioned, it's not very easy to discover these extrasolar planets. It's not trivial to discover these extrasolar planets, but it's not impossible either. Through techniques like radial velocity method, transit method, to direct imaging, etc., astronomers are now succeeding in discovering these extrasolar planets. So the next time you look up into the night sky, and when you see these twinkling stars in the night sky, hundreds of them, thousands of them in the night sky, in your mind's eye, you should imagine that every single one of those stars have multiple planets going around it. Okay, there are probably more planets in our galaxy than stars. If there are 200 billion stars in our galaxy, then if each of those stars has one or more planets around it, that means there are more planets than stars. So this is a very, very important realization that has come about in the field of astrophysics, in the field of science, in the last 20 to 30 years. And this discovery, this fact that there are more planets than stars in our universe, that feeds to this question that we started off with on whether we are alone in this universe or not. We don't know the answer to that question yet, but if planets are more common than stars, and if there are so many planets in our own galaxy, and if our universe has billions of galaxies in it, then it is possible, just from the probability argument, it's possible that there are maybe at least one or two planets where conditions are favorable for life to emerge, for life to evolve and survive. So maybe there are habitable worlds elsewhere in the universe where life is present. Whether the life on those planets would have evolved and produced intelligent beings like humans who are asking these questions, who are going after these investigations, that we don't really know. So finally, I just want to leave you with this very fascinating quote from Arthur C. Clarke, who was a science fiction writer, who was also a scientist in some sense. He was trying to give an answer to this question of whether we are alone in this universe or not, to which he said there are two possibilities. Either there is a cosmic loneliness to our existence, either we are alone in this vast universe, or maybe we are not. No? Both are equally interesting or maybe equally terrifying possibility. If we are alone in this entire universe, then that means that Earth is a very special place, where life is present. And if life on Earth were to vanish, that means that there will not be any more life in the entire universe. But if we are not the only sentient beings, if there are intelligent beings elsewhere in the universe, that's also very, very interesting. What does that mean to our whole existence on planet Earth? So with this, let me stop the presentation and I'll be happy to take questions. Thank you.
Thank you. Thank you, sir. We express of our deepest gratitude to Dr. Anand Narayanan, Professor of Department of Earth and Space Science IIST, for taking time out from his packed agenda to spend with us today.